Okay, welcome. For the people who are joining us by Zoom today, I just put on my AirPods and they were dead. They've run out of batteries. So I probably, if I'm standing right here, I think I'm using my laptop now for the audio. You'll probably be able to hear me fine. I tend to wander though. So, I won't be reading the chat, but say something if you have trouble hearing me. I'll try to stick closer to the table than I usually do on most days. Announcements. There's a Kappa due tomorrow. There's an exam coming up already fairly quickly. Exam 3, covering our thermodynamics section, is next Friday. It will work the same as the first 2 exams. I'll post the equation sheet in the next day or two. We will have another Kappa set due next week it will be all the Kappas, including next week's Kappa, that will be covered in this exam, starting with thermodynamics and ending with thermodynamics. So I think we'll get through all of our thermodynamic stuff by next week, which is why that's when I have put exam 3. So be aware of that. Don't be surprised. Come in next Friday and see an exam in front of you. As before, if you would like to take this exam by remotely, not here in the room, please let me know in the next couple of days by the end of the week, so I can, if it's a large number of people, I may have to do something slightly different. If it's not a large number of people, then we can do it the same as we've done it before, which is have those people pick at the same time and just do it on Zoom. Questions about logistics or Kappas or exams or Thanksgiving? Yeah, so we will have class Monday of Thanksgiving week. I thought about canceling it or making it online, but it's the last time we really get a chance to get together. And it's not going to be any different really than it will be after Thanksgiving, in that if you want to join us by Zoom, you're welcome to join us by Zoom. If you'd like to watch that later on asynchronously, you're welcome to do that also. But yes, I will plan to be here the Monday after Thanksgiving in this room, giving the normal class. You're welcome to join us in any of the ways that work for you for that week. I understand you don't have a lab that week because Monday's a Wednesday, which is confusing, but we have a Monday, Wednesday, Friday, so it doesn't really make a difference for us.
Okay, are we starting special relativity?
We are going to be moving swiftly towards special relativity after the test. There are a couple of other topics to be covered. I don't remember exactly if we're going to be transitioning straight from here to special relativity, but we're very close. There might be a couple, we might do black body radiation, there's a couple of small little sections that we might get to before special rel, but we're basically jumping right into modern physics after we finish this section. How class is going to work? Yeah, so class will be online synchronous, so we will be meeting at our normal time, Monday, Wednesday, Friday, 1:30 to 2:20. I'll be giving a lecture. It will be live. You're welcome to join me then. You're welcome to ask questions. I hope we have some back and forth like we normally do. I hope it can be somewhat interactive. I will be taping those and posting them in the usual way, so if you would like to take the class asynchronously after break, you're welcome to. As you're welcome to take the class asynchronously now, really, if you want to. There's nothing stopping you from doing that. So I think meeting online synchronously gives us the best of both worlds. Those who feel more comfortable meeting 3 times a week, having that structure, asking questions, being there, having it be interactive can. Those who it works better to do it on your own time, in your own place, in your own way, still can do those things. I think it's the best of both worlds. So as far as the lecture, that's pretty much how it's going to work. Kappas will work the same. They'll be due at the same time. I'll have office hours, I assume. I could move those up. I might send out a survey asking if there are other times for office hours that work for people, because my schedule will free up a little bit. I could move them around if we need to. but we can think about that moving forward. The only other thing would be the final exam, and I haven't thought about, I've given it more thought, but I haven't made a final decision about how that's going to work. I will let you know before we break for the break how that's actually going to work. Other questions? Okay. By the way, fresh cranberry sauce beats canned cranberry sauce any day of the week. Just in case there were Thanksgiving questions that we had to get through, that's my emphatic opinion. Obviously, there are people in the world who disagree. Probably people in this room who disagree. Which is okay, we're allowed to disagree, but you're wrong. Okay, where were we? We were talking about adiabatic processes. So adiabatic processes, by the way, if you're here, please do this class sentence thing. I'm going to close it in a minute. You don't have to write this down. I'm just reminding you where we are. Not adiabatic processes. And we define that to be Q equals 0. No internal, no net heat in or out. I probably should have put this slide up last time. We did 10 minutes of straight calculations to get to the result, which was that for an adiabatic ideal gas, if you change the pressure, the volume changes by 1 over V to the gamma. Or V is proportional to P, then negative 1 over gamma. They are the equivalent statements. And if you remember, gamma is defined to be F plus 2 over F, where F is the degrees of freedom, and that turns out to be the ratio of the specific heat Cp over Cv for the particular thing. For an ideal monatomic gas, where F is 3, that's just 5 terms. Okay. But I always want to bring this back to what physically is happening. What does it look like? What does an adiabatic process look like? What should you be thinking about in your head is happening when an adiabatic process happens? And I probably should have, that's not it. Probably should have put this up last time. There we go. How would you go about having a gas do an adiabatic process? Well, we have our cylinder with gas in it, and we have some piston on top, a movable slide, it can slide up and down. And in this case, so we've imagined having this thing in thermal contact with hot temperature baths and cold temperature baths to remove or add thermal energy to the system. In this case, Q equals 0, so we have nothing of the sort. So what is changing in an adiabatic expansion? Well, you could imagine there being a weight on top of this thing, on top of this lid that's holding it down, and you could imagine removing weight from that lid. What's going to happen? There isn't going to be as much force and gravity. There will be the gas should expand because the pressure from below isn't going to be changing. And so the gas will expand, work will be done, and Q will be 0. This is what happened. This is an adiabatic expansion. This is what you should be thinking of. If you wanted to set up a system to do an adiabatic expansion, you could do something like this. Isothermal expansions are actually much more difficult to do because you both have to be taking shot off of the top and you have to be adding or removing energy from the bottom as it moves up to keep the total energy 0. And you have to be doing it in exactly such a way that the temperature isn't changing. That's actually a lot harder to do. This is a much easier process to physically do than what an isothermal one would say. Okay. So this gives us, if we know how the pressure is changing in an adiabatic process, we know how the volume is changing also in an adiabatic process. We can, if P goes up by a factor of 2, then V goes down by a factor of 2 to the gamma. Okay. So we can say some other things. Now that we have this law, actually the other ones come pretty easily. Our ideal gas law says that PV is proportional to T. PV equals nRT. So that must mean that we know that P is proportional to 1 over V to the gamma. So this becomes, plug this into here, and you get V over V to the gamma. Must be proportional to T. I've got gammas and proportional two symbols now, which I forgot to plug in. Sorry, guys, I lost you. Don't know how long you were gone.
Only a few seconds, but
Okay.
for the past couple of minutes, you have been cutting out pretty bad.
Uh-oh. Okay. I have now
your
plugged
voice,
into the wired internet, so hopefully that will all be better. Did you catch what I was saying here? We've got adiabatic process can be done just by removing lead shot from the top of this and letting it expand as it normally would without adding any particular energy to the system. And now we're thinking about, we know how P and V are related. Now we want to know how V and T are related and P and T are related, right? If we know all those three things, we can get all the other ones from anything. That's the complete set of things we need to know. So that's what we're doing now. So we know that PV is proportional to T from the ideal gas law. I can plug this in for P, and I've got this thing, and that will give me this, that T is proportional to V to the 1 minus gamma. If you do that, you have a V and a negative gamma. Multiply those two, you get a V to 1 minus gamma. That's how T and V are related. We also know we can plug in that P is proportional to 1 over, that V is proportional to P to the negative 1 over gamma, and that will give us that T to the gamma is equal to, proportional to P to the gamma minus 1. Those are all of your adiabatic dependencies on how things are treated with other ones. Once you get one of them, you can use P equals NKT or NRT to get all of the other ones here. So, how does this look on a PV diagram? We know that as volume goes up, pressure must go down. As volume goes up, pressure must go down. What does the temperature do as volume goes up? It will not. That's an isothermal process. This is not an isothermal process. And in fact, we know that T goes as V to the 1 minus gamma. What is true of gamma? It's Cp over Cv. Is that a number that can have any value? It has to be bigger than 1. Cp over Cv has to be bigger than 1. Remember how we define these two. The ratio is F plus 2 over F. No matter what you make F, that's always going to be a number that's, the bigger you make F, the closer it's going to be to 1. But it can never be a number that's bigger than 1. And so, it must be the case that gamma, 1 minus gamma, must be a negative number, even if it's a very small negative number. And therefore, what must happen is T to T as you make V get larger. It has to get smaller. If you take any number and you raise it to a number that is negative, that is negative, that number has to get smaller. Any positive number. And volume can't be negative, so we're stuck with positive numbers. Right? So as volume gets bigger, temperature must get smaller. Just based on the formulas we've just written down. So what does that mean for the motion on the PV diagram? We know Right? We can remember what our isotherms look like, right? If I have an isothermal process, remember that is a 1 over V curve on these particular diagrams. We've written these down many times. Those are what our isotherms look like. Are the adiabats steeper or shallower than those isotherms? If I increase the temperature or the volume, my temperature is going down. So if I start here, let's say, if I start here, say, where is that adiabat going to take me? Well, we know as we increase V, the temperature has to go down. And we know that this is a constant temperature thing. So as we increase V, this is going towards hotter temperatures. The higher you go on this chart, the hotter you go. And so the adiabat must be steeper than the isotherms. Because as you increase the volume, the temperature goes down. So the adiabat is going to look something like this. And sure enough, when we look in the textbook, bam, adiabat, Q equals 0. As you increase the volume, the temperature has to go down. The bigger you make F, the shallower it gets, but even if you make F equals infinity, it's just going to be following the adiabat. Or following the isotherm. It can be no less steep than the isotherm. Make sense? I'm seeing a lot of blank stares. The thing to know, I mean, obviously this is important to know. It's important to know how those isotherms go, P proportional to 1 over V. It's important to know how these adiabats go. They're steeper than the isotherms. Those are important things to have in the back of your head. Where that comes from, though, is simply these relationships that we've just derived. How P is related to V, how T is related to V, and how T is related to P for these or these adiabatic processes. Okay. Okay, let's go back to our kinetic theory of gases section. We know that at a given temperature, the average, the RMS velocity of the particles in the gas at a temp T, V RMS is given by, we derived this equation in class, the square root of 3RT over capital M, or if you like it, physics terms, 3KT over little m, where remember R is the gas constant, K is Boltzmann constant, M is the molar mass, and M is the mass per particle. Big M is the mass per mole, little m is the mass per particle. Right, M equals mass in atomic mass units. Little m is mass in kilograms. Okay, are all of the particles in a gas though moving at that speed? We never really circled back at this, did we? I had to think all weekend about how particles can move faster than the sound, and we didn't really talk about that one. I don't think we did. Let's circle back to that. How is it possible? We even did the calculation for nitrogen molecules in a room temperature. nitrogen atoms, and we made the jump to nitrogen molecules and found that it was really high, higher than the speed of sound. How is that possible? Not gonna do it. I mean, there is no magic answer to this. The speed of sound isn't really a limit, right? Things can move faster than the speed of sound. They just produce shock waves. But we're not talking about things moving in bulk through the air that we're breathing, right? It's really hard for things to move through something faster than the speed of sound. It's not hard for individual constituents of that thing to be moving faster than the speed of sound, because they're not interacting with the other particles in any of the same way as an airplane would, or a roller or anything microscopic. They are just bouncing off other particles. And they're kind of like confined to their own little cube box. It's not really true, but you can kind of think of it that way. And so they're free to bounce around inside their box as fast as they want to. There's no bulk motions or shock waves that get set up by doing that. And so it's just a completely different thing to think about the particles themselves moving around inside the matrix and something moving through the matrix at that same speed. Yeah, how fast do electrons move? That's a great question. I don't know that number off the top of my head, but it's much faster than these atoms are moving around. Exactly right. Exactly, same concept, same concept. So, right, so that's that thing. Go ahead.
So then, like, when, for instance, like a sound wave is passing through
Yeah.
molecules, they're moving up and down, creating this pressure difference, right? Or they're moving.
It's a compression wave. It's not a transverse wave. But yeah, they're getting pushed back and forth as that wave. That's right. But that's a bulk motion of all of them. But you're right. That bulk motion is way slower than they're moving within their individual components. That's right. But it's an ensemble motion, right? So on average, they get as the compression wave pushes them in this direction, they're moving a little bit more in this direction. As the compression wave moves them backwards, they're moving a little bit. And it's not that the particles are moving that fast in the wave even, it's the wave that propagates that fast, right? And it's different particles that are in the wave as it moves along. So
That like the average movement, like if you take like one particle and the sound wave is passing through that particle, it's like it's moving incredibly fast. But
right.
The average movement,
exactly. The average motion of all 10 to the 20 particles that are in the square centimeter, on average, are moving back and forth as that sound wave propagates. That's right. At the frequency that the sound wave is propagating. That's right. So now let's go back to the question at hand. Now, are all the so we can calculate this velocity? Are all the particles in the gas moving at that speed? No, it's an RMS. It is a average. It's actually the average of the squared square rooted. This is the average of the squares of the square of the velocity square rooted. That's what the RMS is. But there will be some particles that are moving faster than that. There will be some particles that are moving slower than that. It should be a distribution of speeds. So let's think about what that distribution is. So let's think about, so this is a nice picture animation. If you follow the red particles, you can see how even they, as they bounce around this two-dimensional box, change in velocity rather a lot as they get bounced around. This is similar kind of process that's happening in a three-dimensional way in every square millimeter of, every cubic millimeter of gas. So not only is there a range of speeds and velocities, every particle average will experience those range of speeds if you wait long enough. They're all changing all the time. So, right. So let's try to figure out what that distribution looks like. That's our next step. Figure out what that velocity distribution looks like for a given temperature. So Boltzmann, whose name we now attach to the K constant, determined something rather interesting, and he found. I actually don't know the experiments that led to this. I'm curious. I should look it up, but I haven't. The probability of finding a particle with energy E is proportional to E, lowercase e, as in Euler's number, to the capital E, as in energy, over kT. So let's think about what this looks like. In velocity space, let's train this to velocity space. We know that E is 1/2 mv squared. And so the probability is proportional to E to the negative 1/2 mv squared over kT. So let's think about this in velocity space. What does this look like? It actually looks something like this. So you've got some average velocity that they're moving at. Velocity is a vector, though. So you think about how this works. You've got, so this is the probability of finding a particle at a given velocity. Now, if you increase the temperature, the odds of finding a particle with velocity higher is going to be higher. This is going to expand as you increase the temperature of this gas. What is the this is the distribution, right? What is the average of these velocities? I don't know if you can see the numbers on there, but it's centered on a particular number, which shouldn't be surprising. These are velocities of vector quantity. So they're moving in that direction, some moving in that direction, some in that direction, some in that direction. What's the average going to be? 0. Exactly. On average, our gas isn't moving. It's there. On average, this chunk of gas isn't moving. It's just there. On average, this chunk of gas isn't moving. Unless you have a wind blowing on it, we're not going to consider the average is 0. But the average speed is not 0. And so really what we want to know is, what is the average speed of the particles in this gas? And that's sort of what we were talking about with VRMS. How are we going to get this average speed from this velocity diagram? We need to do some sort of integration over integrating the height of that probability distribution times the, in the case of a two-dimensional sense, the area encapsulated by your dV ring around it. It's going to be some interesting, you can think about mathematically how that's going to work. And maybe this picture helps you when I write down the next equation. Really, this is a very hand-wavy way of trying to write down the next equation and explain where the terms come from. So this is really in a three-dimensional sense. This is a two-dimensional representation of a three-dimensional thing. So in a sense, you're actually doing a volume integral, multiplying the value of that probability as you go out, which is getting smaller, times the volume of a shell containing that particular velocity getting bigger as you go out. And you get this equation. Speed distribution looks like this. Um, 4 pi m over 2 pi. We've got some integration constants because If you multiply probability distributions from 0 to infinity or from negative infinity to infinity, it has to be 1. And so you get some normalization terms up front. All the 3/2 power times v squared times e to the negative 1/2 mv squared over kt. And this v squared term comes from, well, never mind. Doesn't really matter. So let's think about these actually. There's a 4 pi v squared term. What is that? That is the area of a spherical shell around that velocity distribution with velocity v. In velocity space with velocity v. You've got this e to the negative 1/2 mv squared over kt comes from the height of the distribution. That is what we were plotting. The probability is a function of velocity away. And the rest of this thing to the 3/2 term is a normalization term. Because it has to be the case for a probability distribution, we need to have the integral from 0 to infinity of probability of finding a particular particle at v, at velocity v times dv has to be equal to 1. Otherwise, it's not a very good probability distribution. So that's just a normalization term to get the units to work out right and to make it so that the integral of this integral is 1. Okay, so again, this is something that we're going to call PV. This is the probability of finding a particle at a particular velocity given the temperature of that gas and a mass of the particle. What does this function look like? Well, there's two terms that are depending on v. There's a v squared term, and there's an e to the minus v term. E to the minus v squared term. One is a parabola, and one is a rapidly descending exponential function. If you put these two things together, you'll get a pretty good idea of what this thing looks like. Here's a parabola, here's a rapidly descending exponential function. Put the two together, and you've got the distribution. That's what it looks like. You know, without the overlapping things in a continuous way. So, v squared term, e to the minus v squared term, put them together, you get this thing. Here's a better diagram of it. Where you can see actually how this all works. Okay, what happens if T increases? What does this curve do if temperature increases? Think about it. Is the velocity going to be getting higher or lower? High. Has to be shifted to the right at some level, right? It's the same curve, it just has to be shifted to the right. How about up or down? Well, again, the integral just has to go to 1. So as you make those velocities bigger and bigger and bigger, you actually need to make the probability lower and lower. It actually will, it should. Well, let me show you. This is what it will look like as you go to hotter temperatures. Here is the same gas with at 100 Kelvin, at 200 Kelvin, at 400 Kelvin. As you know, as you make a gas hotter, the particles inside it, on average, will be going faster. That's what this is showing. The only reason why the peak has to go down is because the integral under this curve has to be 1. And as you make those numbers bigger and bigger, you have to make the peak come down lower. You look confused. It should look familiar. It looks a lot like, I don't know, maybe the black body curve, yes. Except in the opposite way, right? As you make the temperature hotter, it goes in the opposite direction. It looks very similar to that. It's a completely different thing. If you've seen the black body spectrum, it looks a lot like this. And it functionally is very similar to what we've just written down. In fact, it might be identical in some ways. But this is a probability of finding a particle at a particular velocity and not the number of photons coming out at a particular wavelength at a particular temperature. It's just a different thing. It looks very similar. Okay, so that's if temperature increases. What if the mass increases? Let's think about this. So we've seen if temperature increases, what happens? What about if mass increases? As you can see, there's two masses and there's two temperatures in this equation. And they are always on opposite sides of the numerator-denominator pair, or in both places they show up. Right? Temperatures on the bottom, both in the exponential and in the frequent count term. Mass is in the numerator on both of those things. So mass is going to have exactly the same effect on this chart, just in the opposite direction. As you make the mass bigger, the velocity should get smaller. And voila, here we have the average, for the same temperature now, we have the average velocities of particles in that gas based on their masses. Here is helium, which has an atomic mass of 4. Here is neon at 20. Here is argon at 40. And here is xenon at 132. The more massive particles have to move slow. Why? Because temperature is a measure of the average translational kinetic energy of a substance and the particle. And so the more massive you are, the slower you're going to get the same amount of energy at the same temperature.
Does this mean that, for instance, like a higher mass or lower temperature is more likely that you will find a particle at a specific temperature, just because the curve is less?
Right. That brings up an excellent question. I don't know if the Zoomers heard it, but I want you to repeat it because it leads me exactly into what I'm going to talk about next. The question was, is it therefore, I assume you're saying since this is so much lower than this, is the probability of finding a particle at a given speed here lower than it would be at finding a particle at a specific speed? Good question. What is this P thing? Because what is the probability of finding, even for this blue curve, a particle going 1,000 meters per second? You might say, oh, you just have to come over here and it's a little less than 0.001. That's not the case. The odds of finding a particle at exactly 1,000 meters per second, and I mean exactly 1,000 meters per second, is 0. Right? 1,000.0000000, however far you want to go out, the odds of finding a particle at exactly that speed is 0. All of these, anytime this may be the first time you've encountered probability distribution. They are weird things. And in fact, you really can't say, it doesn't make much sense to say what is the probability of finding a particle at a given speed. That isn't really even a sensical thing to say. You would have to say, you would have to say, what is the probability of finding a particle with a speed between this and this? You have to integrate this to get a true probability. It's not a probability curve, it's a probability distribution function. And probability distribution functions have to be integrated in order to get actual probabilities. So, yes, the answer to your question is, for a given delta V, you are more likely to find particles in that delta V near the peak of this distribution than you are near the peak of this distribution. But that delta V is a really important part of that conversation. Right? And if you scaled that delta V to be proportional to, say, VRMS, then it would be exactly the same. Does that make sense? Okay, that was a lot.
Question for those charts.
Yeah.
For those charts, so all those charts are saying is like, I guess the math one would be, if you go to the peak, it's saying 50% of all your speeds are below that velocity, and 50% of all velocities are much greater than that.
Ah, interesting question.
So you're saying that's like if you did the delta V, so if you took peak to peak, you would have end up with the same chance of finding a particle in that given parameter.
Okay, I agree with the second thing you said, but not the first thing you said. So if I were to take the peak and integrate from 0 to that peak for any of these peaks, I'm going to get exactly the same number, right? Because it's the same function. We're just scaling it in different ways. But it is not the case that if I take this peak and integrate this side, I get exactly 50%, 0.5. I do not. This is not a symmetric curve, interestingly. And in fact, that's my next. You guys are anticipating every single thing that I'm going to explain next from my notes, which is fantastic. Excellent. These are just the inverse. Okay, right. So where does VRMS land in this function? Where is the VRMS? Let's see where it lands. That's the next. Oh, that's not. Where's my? I thought I had a VRMS on here. Oh, I do. It's on here. This is the peak of the distribution. This is the mode. This is the most probable distribution. The average velocity is x. Since this tail extends, this stops at 0, but there's a tail out here to the positive that extends to non-zero values well past the delta, right? So this peaks at 400. This is non-zero well past 800, right? So this leans a little bit to the left, if you like. It's got a tail to the right. Got a tail to the right. It leans to the left, maybe a little bit. So the mode is here. The most probable velocity is there. But the average velocity is a little bit higher than that. And the VRMS value is a little bit higher than that yet. Because, as you remember, VRMS is not exactly the same as V average. If this were a perfectly symmetric distribution, then all three of those would be in exactly the same place. But it's not, and so they're not. Okay, so when you say VRMS, yes, you're talking about the true average of the square root of the average of the velocity squared, but that's not where the peak of this distribution is even. That's not the most probable value, because you've got some of them out here on this tail that are averaging quite a bit more than that. And that's also why the VRMS, when you square those values and then take that average, these guys contribute a lot more in that one, because you're squaring it, than these guys do, and so the VRMS gets pushed even a little bit further out than the average does.
Quick question on those three lines.
Yep.
So does that mean, so the way that thing works for the peak, you're saying, so it's saying it's more likely to find higher velocity particles that is on low motion VRMS is to the right of the graph or not?
It's more likely, yeah, yes. The average is probably where you get a 50% probability in this, right? This is probably the breaking even point where if you integrate to the left of this, you get 0.5, and if you integrate to the right of that, you get 0.5. The peak is not where 50% is. It's a little bit to the right of it.
The likelihood of that is saying a particle at 0 really becomes 0.
Yeah, this says the particle of finding a chance of finding a particle at 0 are basically 0. That's right. That's right. Yep. Okay. So we can actually write, we've already written down what VRMS is as function of temperature, but you might be interested to know what the average velocity is as function of temperature. And you might want to know what the most probable value of velocity is as a function of temperature. Those are both numbers we can write down. Let's go ahead and do that. V average is not VRMS, but V average is equal to, again, this is the integral from, how do you find an average of something that's a smooth distribution? You take the integral of it over all velocities of the value times that probability function times dV. If you do that, I mean, you can do this for fun if you want to. You don't have to, though. I'm going to write down the answer. It's kind of a messy integral. You get square root of 8 kT over pi m, or square root of 8 RT over pi big M, if you want to multiply it. Most probable, where that thing peaks, V peak, I'll call it V peak, is square root of 2 kT over M. And if you like to multiply it, that's 2 RT over big M. So if you don't, so again, VRMS, there's a square root of 3 in there. V peak, there's a square root of 2 in there. The average, there's a square root of 8 over pi in there. And you have to trust me that 8 over pi is between 2 and 3. So the average velocity is between 2 and 3. Is between the peak, the most probable. By the way, you get the most probable by taking the derivative of setting it equal to 0 and solving for V, which is also messy, and I don't recommend doing it. But you can if you want to. Okay, now, I've already said this, but I want to emphasize it again. This PV thing is weird. As we've already discovered, it is not a probability. Only discrete things have probabilities. The odds of rolling a 5 on a 5-sided dice. Continuous things do not have straight probabilities. They have probability distributions, and that's where we're at now. Right, so I've already said this, but I'm going to say it again. Only discrete things have probabilities. Well, that's not true. But, so the odds that a particle will have a velocity v equals 500 meters per second is 0, because there is no room there for anything. 500.000000, there will be 0 particles that have that exact probability, that exact velocity. You have to integrate over a range of velocities. To get a probability. It's a probability distribution. So really, you want to go something like integral of PV times dV from V1 to V2. That will give you the probability that a particle has a velocity between V1 and V2. It isn't even a unitless thing. It has units, so it can't be a probability. What are the units? The units of PV are the units of, we've got mass on top, we've got mass on the bottom, we've got velocity, meters squared per second squared, velocity squared on the bottom, all of that to the 3 halves, times a velocity squared, meters squared per second squared. The kilograms go away. We've got a second squared per meter squared that gets multiplied to the 3 halves power. That gives us a seconds cubed per meters cubed. All of this stuff boils down to that. And I've got a meter squared per second squared, and I've got a seconds per meter. That probability distribution has units of seconds per meter, inverse velocity. which is weird until you think about what this means, right? Why does it have to have this particular units? Because we want to, this is not surprising. Why not? Because we need to integrate PV times dV and get a probability, which is unitless. This probability distribution function, I've labeled it sub v because it's a velocity distribution function. It has to have units of inverse velocity because we have to multiply by a dV and integrate to get a unitless probability function. Actual probability. And probability has to be unitless. Okay, I am out of time. So this is a good introduction though, because next semester you're going to be thinking a lot about probability distribution functions. And so here is over things that are very weird and esoteric and hard to wrap your brain around. Here at least is a probability distribution function of something that is easy to wrap your brain around, how fast things are moving in a gas. So we'll think about, there's a couple of others that we're going to write down this semester as we go on, but there it is. See you Friday.